Chaos hunts the spark of endless suns, whose light will die in my crushing grasp.
Look at this purple Giga Chad that's built like a brick shithouse. He's unequivocally one of the strongest characters, not just in Dota, but all fiction. This character casually benches the massive Jupiter, hits a lat spread, and mogs every other hero on the map. This walking cosmic violation genuinely needs to be buffed in game because Valve are seriously underplaying how strong his kit would actually be. This may have started out as a teensy little bait. We are still going to go over how powerful Enigma is, but in real life, not in the game itself. And I think it's obvious which ability I'm referring to here when it comes to power. His insane teamfight ult, Black Hole. Let's just imagine that this dumbass game is real for a second. There's only a certain few heroes that could survive Black Hole. Even your mum would struggle against this big black beast that doesn't even let light escape the fate past the event horizon. Here's an example for you. It's a little bit like when you accidentally make eye contact with a random crackhead on northern train lines and aggro them like a lane creep. Once you've made the mistake, you've set your fate in stone. So let's get into it. My name is Shiguchi, and this is the physics of a void incarnate, Enigma. Source Engine works on different base mechanics from what our world does, but luckily it has a unit of distance that we can use called the hammer unit, which is what we're going to be relying on mainly to find most of our measurements to do our calculations. We then convert from hammer units to a more standard unit of measurement. This way we can apply game physics to real life. This is why I'm using surf footage. It's a good example of how Source's physics engine works. CS has these weird gliding effects because of a physics glitch within the engine itself. That's related to the way that the game's geometry is calculated. Hammer units depend upon the game's parameters, but most of the time it resolves around 1 inch. So all I have to do is convert from freedom units to metric. So now that we've gone over how to convert between the units of Source Engine and real life, all we need to do now is measure the dimensions of Black Hole within the game. Let me quickly explain what I'm doing here. I'm trying to find the radius of the event horizon of the black hole. That's the black part of the black hole. And I actually found out a pretty neat way of doing so. First, I took the radius of the AoE of black hole, which is the red line right up to the very edge there. The green line is the black hole's diameter. All I have to do is keep copying the green line until it fills out the red, and then however many times I've done that should give me the ratio between their sizes. All I need to do then is take the known units of the black hole's AoE and divide by this new number. Overall, this should give the radius of the event horizon. This is basically a more informed version of pixel counting, though this method does have its drawbacks. You can see here that it's overshot slightly, and I actually kind of need to eyeball it to see how much it's overshot by. Now, although we have been using hammer units, that is not the same case for models within the game, as they get scaled off the hammer units instead, so it's a ratio more than an actual measurement. This could also be down to human error though, like a parallax error or even a measurement error. For the sake of scientific accuracy, I've done this method 3 times with 3 different images, and I always got a ratio of 7 and a bit. So if the diameter fits in 7 times, that means the radius fits in 14. 420 hammer units divided by 14 gives me exactly 30 hammer units. Nice. So now that we've found how big black hole is in the game, we can convert from those hammer units to meters, which is roughly 0.762 meters. Awesome, after all that, we've finally got the radius of the black hole. And now that we've done... for this bit, we're changing up the style. And now that we have found the radius of black hole, we can officially calculate the power of Enigma. Well, at least his ult anyway. Okay, a quick model of what we're going to be using. We're going to be using a Schwarzschild black hole, which is the most basic type of black hole that you can get. It's got no charge, it doesn't spin, it's just a pure mass that has been condensed down into an infinite point. I chose this because mathematically, it is very simple. Now, Enigma's black hole does appear to rotate, and it might even have charge, as you can see from the little jet on the top there. I have been looking into whether to model this as a Kerr black hole, but I've decided against it because I actually need to get this video out. Who knows, we might revisit this in a later video when I have more time. Right, so I've got the whiteboard behind me. Let's get into doing some calculations. So the equation for a Schwarzschild black hole is as follows. This is for its radius anyway. So that's the gravitational constant, the mass of the black hole, divided by the speed of light squared is equal to its radius. We have the radius, 0.762. So we're going to put 0.762 into there, but first we want to rearrange for mass. RT squared over G is equal to M. And that should give us the mass of the black hole. Now, it's going to be very big. So if we get rid of this, R is equal to C is equal to 8, that should be squared. G is equal to 6, 7. And we're just going to stick that into the calculator. So taking all of these and put them onto there. I haven't got the best whiteboard set up, so I'm going to do all the calculations on the screen from now on. Hopefully, I'll be able to change this at some point. It's standard to show units, and I've also fixed some values that I got wrong on the board. So plugging values in. Sheesh, that is massive. And although it's not quite benching the mass of Jupiter, which is what I had originally hoped for, it is still quite close. It's about a quarter of the mass, so still huge. It's actually absurd how large this mass is compared to how small the radius is. And we can see the mass of Jupiter here at 1.898 times 10 to the 27 kilograms, making the mass of Enigma's black hole 0.271 Jupiter masses. But knowing the mass doesn't really tell us anything. What we're really interested in is the force. Unfortunately, we can't get the force because we don't know the masses of the heroes either, so if we're going to use Crystal Maiden for example, we'd have to either lie or try and find some actual mass for her. But there is a different, more interesting way in my opinion. We can find out the acceleration due to gravity. So if we go back to a section earlier here, we can actually see the radius at which black hole has an effect. And we can use the equation that I've just written on the screen to find that acceleration. And luckily, we already know this radius in hammer units. 420 baby! So let's once again convert between hammer units to meters. So characters are about 10.7 meters away. At this distance, we should be using GR, but... Hi guys, Saguchi from the future here. It turns out that maths doesn't care about how I think or feel. It made me use it anyway, otherwise none of it would have worked. So... let's plug the numbers into the equation. We take the gravitational constant times by the black hole mass, divide by the radius squared, giving... Holy fuck! I don't think you quite understand how insane that is. So I'm gonna put this in terms of G-forces. Most people have a good idea of what it would be like to weigh double and to then keep putting that extra weight on. So to find out what it would feel like in body masses, we just take the acceleration that we just calculated and divide by the acceleration due to gravity on Earth. And boom, we now have the G-force. For reference, if you weigh 60 kilograms under this G-force, it would now feel like you weigh 14.2 pyramids of Giza. And this all comes from the fact that the radius on the bottom is squared. So, with that being said, section 4, the aftermath. So, in this section, we're going to have way less maths. Hell yeah. This is officially where the fun begins, because now we can use all the cool visual representations. I've calculated all hard stuff like relativistic effects, energy, temperature, and line spectra emissions. I'm just going to present it to you in a way that's fun and engaging, right? No one's bored yet, right? But we need to start with a little tangent first. How I used general relativity. I tried my hardest, and I mean my hardest, when I say I've tried to avoid actually properly using it apart from trying to get the Schwarzschild radius. But it just turned out that for this section, there was a lot of things that I needed to calculate that genuinely required it, so I had to bite the bullet. I would like to point out that I have in no way learned general relativity, like being able to use the field equations to solve for a metric. Much smarter people than me, like Schwarzschild, were the ones that derived these equations, and then I have used them for our black hole. Don't get it twisted, these equations were still a pain in the ass to be able to manipulate and use. It's not easy at all. It's still taken me hours of scrolling the physics stack exchange, using ChatGPT, and looking at books just to be able to use these equations properly. Right, so now that's out of the way, we can go back to what we talked about earlier. So the acceleration that I calculated using Newtonian gravity is only correct for scales not near the black hole. And when I'm saying not near, I'm talking about hundreds of meters away. So that's where we're going to start. Here is a scene of New York. This is Enigma, 574.98 meters away. Now, you might be wondering, why is that the number that I've chosen here? And it's simple, really. That's how big the map on Dota is. So if you were to stand on one corner and Enigma was to stand on the other, that's how far away he would be. So we're really taking the max distance of the map here. By the way, I got this distance because the map of Dota is 16,000 by 16,000 hammer units. I then used Pythagoras to get the total radius. Hey, look, I said there would be less maths, not zero. So now that we've got our scenario all set and pictured, let's simulate what the black hole would look like when Enigma drops it from this far away. He's going to drop it in 3, 2, 1. You're probably wondering, where's the simulation? And I would like to say to you, that was the simulation. You would be pulled into the black hole so fast that your neurons wouldn't even be able to register what just happened. To the character that was far away, this all started and ended in 80 microseconds. That's from being at rest, over 500 meters away, to hitting that event horizon. To the character falling, they would have hit near light speeds, and once beyond the event horizon, way beyond it. If you weren't already dead, you would then hit the singularity not much sooner later. The best way to visualize what exactly happens is to assume that we are an observer, watching from a distance. That way we can see what happens to the characters without being part of their demise. Between the 500 to 300 meter mark is crucial. In just a few nanoseconds, the character would undergo such a violent shock that their entire body would superheat to approximately 170,000 degrees Celsius. This is caused by the tidal forces, where parts of the body that are closer to the black hole feel more force. This rips molecules apart, turning the character into one long string of matter and energy, known as spaghettification. The tidal forces stretching out the body causes friction, which makes black holes some of the most efficient engines in the universe. The intensity of the heat and the radiation that comes from the character as it's turned into a plasma is equivalent to a thermonuclear explosion. Every bit of distance travelled towards the black hole exponentially increases the amount of heat released. Extreme amounts of hard UV radiation and soft X-ray radiation is released between the start and the 300 meter mark, with intensity and frequency increasing the closer the character gets to the black hole. Past the 100 meter mark, we start to see general relativity take over. Minute time dilation and Doppler effects would be noticeable to sensitive equipment, all while the acceleration of the character continues to increase as they get closer to the black hole. To us, we see these characters get to a maximum velocity of roughly 40% the speed of light, before then rapidly slowing down, like almost within an instant, just before they touch the event horizon. And this was all for the outer character. The furthest one away, Now we'll talk a little bit about what happens to the ones that are close to the event horizon. Their journey takes 0.2 microseconds to hit the event horizon, so 2 orders of magnitude quicker than the far away character. So instant death, but more. The energy densities at this point are absolutely wild. They're able to split atoms and fuse them, causing hard gamma ray emissions. This is almost the point of quark gluon soup, but let's just stick to thermonuclear goo, the rough temperature being 26 billion degrees C. We, as observers, would watch them get to about 90% the speed of light before they quickly slow down just before they hit the event horizon. Now, you might be wondering why both the faraway character and the close characters all seem to slow down just before they hit the event horizon. This is because time dilation takes over, and now the light that is reaching us is taking longer and longer to get to us, so it appears that they're slowing down, and we never actually see them cross. Their journey to us never ends. The extremely curved space-time also causes a Doppler shift in the light as well, meaning that the light gets stretched, causing it to change energy and wavelength. Little side note here, we actually don't know where this energy goes, and it's still one of the only times that we ever see energy conservation violated. Aside from all the other interactions that go on during this process that would produce a beautiful spectrum of different photon wavelengths, we as observers would see this gradual shift between gamma rays to X-rays to UV to visible light all the way down to radio signals. As light from close to the event horizon manages to escape little by little, all we see is a ghost of their light that's forever etched onto the side of the black hole that slowly fades away as the light gets redshifted into a wavelength that we can't see. All that will be left of them are the echoes of what they once were in the form of radio waves that some civilization in a distant future will pick up as static on their TV. I'd just like to reiterate one more time for the people in the back, so all the calculations done here are not going to be perfect. I've just used equations that were already available, and I've used them to the best of my ability based upon the knowledge that I gained from doing a Masters in Physics. And to self-glaze a little bit, I did just get accepted onto a course to do theoretical physics for a PhD, so that's very nice. Which, by the way, I should have been working on, but instead I was making this video. Now that we have accurately depicted Enigma's black hole, let me leave you with this. If there is anything that you've learned from this video, it's not that small things are insignificant. Even the black hole, that's less than a meter wide, in a fraction of a second has enough power to destroy Earth and throw off the balance of the solar system. So don't think just because you're small, you're insignificant. For you have more power than you could ever possibly imagine. And the fact that you existed will leave its mark on the rest of the universe's history. Thank you for watching.